Hello everybody, we're going to continue with our understanding of the formation of spectral lines. We're going to continue also using the hydrogen atom, the simplest of all the atoms. We're going to ask ourselves the question of what are all the wavelengths, what are all the energies that a hydrogen atom can interact with? Is there a way to systematically go through this? This is going to be an application of everything that we learned in the previous video, so hopefully this will help tie everything together while teaching us something rather important. So, let's go through the spectral series of hydrogen. What I want to do is, again, I want to start with our Bohr model of the hydrogen atom, which you can see here on the screen. But what I want to do is I want to come up with a systematic way so I can understand what are all the possible energies that you can get from moving an electron from, say, the ground state to the first excited state, the ground state to the second excited state, or from like the sixth excited state down to the second excited state. That could happen, and that'd be an emission line, right? If we're going from a high energy to a low energy, you're going to emit a photon. You could go from the fourth to the first, the fourth to the second, the third to the eighth, the first or the ground state to ionized. So that would be absorbing a photon that has an energy of 13.6 electron volts to the minimum energy to ionize. You can go from first excited state to ionized. You can go from ionized and it could come into the atom, an electron, a free electron, could find an ion of hydrogen and come in and fall into the fifth excited state. As you can see, since there are essentially infinite numbers here, there's a lot of different ways you could play around with this. But each one has a very distinct energy. Each one has a very distinct wavelength. And I want to know what are all the possible photons, what are all the wavelengths of light that our hydrogen atom will interact with? What are the wavelengths? What are the energies of those photons? And what we really need is a good systematic way to map all of them out. So maybe what we want to do is start with something like, hey, let's start with the ground state. That's nice and easy. What about all the photons that can go from the ground state to the first excited state, that 10.2 electron volt energy jump? By the way, don't have to memorize these energies. I just have them down here. Maybe we want to go from the n equals 1, the ground state, to the first excited state. 10.2 electron volts, calculate the wavelength. The n equals 1, the ground state, to the second excited state. 12.1 electron volts. The ground state to the third excited state. The n equals 4. 12.8. So maybe I want to do it systematically like that. What are all the photons that the hydrogen atom can absorb? Well, first state to second state. N equals 1 to n equals 2. N equals 1 to n equals 3. N equals 1 to n equals 4. N equals 1 to n equals 5. N equals 1 to n equals 6. So on and so forth, all the way up until I ionize. And then do it in reverse for emission, from ionization to the ground state. From the n equals 100 to the ground state, n equals 99 to the ground state, n equals 98 to the ground state, yada, yada, yada. N equals 4 to the ground state, n equals 3 to the ground state, n equals 2 to the ground state, n equals, oh, wait, that's it. We're done. So that would get me all the transitions into and out of the ground state. Now, I personally find it a little bit annoying because I like to draw pictures of how the electron is moving around. So these Bohr models, with everything crammed together in these nice, with all these rings, I find it a little bit messy to work with. So why don't we just sort of like zoom in, since the electron, the minimum state it can be is in the ground state. So let's zoom in on this green box. And then you can see the bottom would have the ground state, and then above that you'd have the first, second, third. Kind of like you're drawing a well, where getting out of the well would be reaching ionization. So let's flip our perspective a little bit to look at the same information in a different way. What's called a electron energy level diagram. Oops, skipping ahead right here. So we want to look at an energy level diagram. So let me flash back and forth between slides really quickly. So notice that I have my ground state. I'm going to put that at the bottom, the lowest energy that the electron can have. So here's my well. The ground state is at the bottom. N equals 1, ground state. And I'm just keeping track of my energies over here. It takes energy to move it out. So this is negative, and then we'll be going towards positive, gaining energy, where we say energy equal, it's free, the electron can leave forever. That's why those are negative. You don't need to know this kind of information. We're just going to come up with a better way so I can easily map all the possible transitions. Okay, so here we have the ground state, and then we have the next allowable state, that n equals 2. Our first excited state is some jump 10.2 electron volts energy higher. So it's higher. And then it's going to be a little bit smaller for the first to the second, and then a little bit smaller, then a little bit smaller, then a little bit smaller, a little bit smaller, a little bit smaller, a little bit smaller. And if you give that electron 13.6 electron volts, it will be free from the energy well, the bottom of this energy level diagram, and it will be ionized. Our hydrogen atom will be ionized. So really, this energy level diagram, we're not going to work a lot with them in class. You'll see them a little bit on homework, but not for quizzes and exams. I just needed to introduce this so you know what I'm talking about. And really, we're just looking at a different version of the Bohr model of hydrogen, drawn in a way where I have plenty of room to start drawing on how I can move this electron around. So I'll be able to draw, say, a line that shows an electron moving from here up to here, from here to here, from here to here. Let's put you back home where you like to live. Okay. And then, of course, the nucleus will be down below. Hopefully now you have a sense of what's going on in this energy level diagram. Because what I want to do is I want to use it to start mapping out all the possible photons that the hydrogen atom can interact with in a systematic way. Let's start with from the ground state, and let's move them up. Let's absorb photons, because to go from a low energy to a high energy, we'd have to absorb a photon that has the exact right amount of energy, 10.2 electron volts, to do this first jump. Okay, so that's what we're going to do. I want to go ahead and note that everything we're going to talk about is about to be an ultraviolet photon, not visible light. Higher energy than visible light, shorter wavelengths than visible light. The way we're going to do this, so this is, we call the systematic approach. Every line that I'm about to talk about, every photon that the hydrogen atom can interact with that involves going from the ground state to a higher excited state, or a higher excited state down to the ground state, we call that the Lyman spectral series. So the spectral series is just saying, let's approach all the photons that hydrogen can interact with in a systematic way, a series of spectral lines that all have a commonality of the ground state. And then it's the Lyman one, because the Spitzer-Lyman, a astrophysicist, was the one that basically mapped mapped this spectral series out. Okay, so we can go from, we'll do absorption first. We can go from the ground state up to the first excited state. We could do it in reverse, in emission, and go from the first excited state to the ground state, where we're going from 1 to 2. Equivalently, we can go from 2 to 1. Ask ourselves, what is that energy? Well, that would require 10.2 electron volts of energy. I could calculate what the wavelength is. That would be a photon. That's 121.6 nanometers. This would be the lowest energy, because notice if I want to go from the ground state to anything above it, that's more energy. More energy is shorter wavelengths. So this is our longest wavelength, our lowest energy photon in the Lyman series. It moves an electron from the ground state to the first excited state. And we start labeling our series from the lowest energy. Since this is the Lyman series, let's go ahead and call them Lyman lines, which will indicate with the letter L. And then we will start numbering to higher and higher energy ones using the Greek alphabet. So the first one would be alpha. So this photon, the one that for hydrogen, it will move an electron from the ground state to the first excited state if you're absorbing it, or it'll move it from this first excited state to the ground state if hydrogen is emitting that photon. We call this photon the Lyman alpha photon. Has a wavelength of 121.6 nanometers. If we could see all the different wavelengths of light, we weren't just limited to visible light, this would be the most common color in the universe. This is the most common photon in the universe, the Lyman alpha. Why? Because hydrogen is the most common element, and it is the most common transition in hydrogen from the ground state to the first excited state. So here it is, the most common color in the universe. If you've ever had that question before, you've been curious, what is the most common color in the universe? Now you know. It's an ultraviolet color, and it's called Lyman alpha. Has a wavelength of 121.6 nanometers, which corresponds to an energy of 10.2 electron volts. Okay, so that was a lot of lead up. What's the next one? From 1 to 3, Lyman beta has a wavelength of 102.6 nanometers. I think I had 0.5, that was a typo in the previous one. It's supposed to be 102.6 nanometers. A slightly higher energy, 12.1 electron volts. Still ultraviolet. Then we'd have gamma, delta, epsilon, and so on and so forth until you reach ionization. Each one a little bit higher energy, a little bit shorter wavelength. And you could calculate what's the shortest wavelength. Well, that would be the 13.6 electron volts to go from the ground state to ionization. And that would give you a wavelength of 91.2 nanometers. Another important thing in astronomy. And you can go in absorption, going from low to high, or you can go from an emission from a higher energy state to a lower energy state. So our Lyman series is every possible transition in the hydrogen atom, every possible photon hydrogen can interact with that goes from the ground state to a higher excited state, or from a higher excited state to the ground state. And higher excited state includes ionization. Let's do that pattern again, but let's just bump it up a notch. Instead of starting at the ground state, we want to know all the possible photons. Let's play that game again with a different set of photons, a different series of photons, a different spectral series. Play the same game. Let's start at a given energy level and then move it to a different energy level. So this one, let's start at the first excited state. So we could go, for this spectral series, we could go from the first excited state to the second excited state. And that would be 1.9 electron volts of energy, the difference between those energy levels. It would be absorbed to move up, emitted to move down. Now, if you want to go ahead and crunch it, you'll calculate that wavelength to be 656.3 nanometers, which is in the visible part of the electromagnetic spectrum, which means the human eye can see it. And we would see this as red, a very nice red color, 656.3 nanometers. So if you want to talk about the color that humans can see that's most common in the universe, so what's the most common color humans can see that exists in the universe? It's this one right here, 656.3 nanometers. Since this is the light that humans can see, we label these as the hydrogen series. So we call this first line the hydrogen alpha line. The technical name for the entire series, where we're going to go from the first excited state to any higher excited state, or any higher excited state down to the first excited state, we're going to call that the Balmer series, since that's the person that mapped this out. But we name the lines hydrogen lines because they are the first ones that were studied simply because humans could see them. So when we looked at all of the absorption and emission spectrum of hydrogen that I've shown you so far, we were looking at the Balmer spectral series, the visible light photons that interact with hydrogen. The lowest energy one, the longest wavelength one, is called hydrogen alpha, and it has a wavelength of 656.3 nanometers. It takes an electron and moves it between the second and third excited states. So going from the second to the first to second excited states, the n equals 2, the n equals 3. Sorry about that. If it's moving up from n equals 2 to n equals 3, from first to second excited state, it absorbed that photon. Hydrogen absorbed that photon. If it moves down from the second excited state, n equals 3, to the first excited state, n equals 2, it emitted that red photon. Okay, so starting, that's the lowest energy one. What's the next one? Hydrogen beta, as we call it, would be 486.1, a cyanish color, a blue-greeny color. And then we'd have hydrogen gamma, 434.1 nanometers, a blue color. And then we would have another blue, hydrogen delta, 410.2, the n equals 2 to the n equals 6, and so on and so forth until you reach ionization. So it'd be 13.6 minus the 10.2, that's right there. So we're talking about 2.4 electron volts of energy, or sorry, 3.4 electron volts of energy, I could just read. And that gives us a wavelength of 364.8 nanometers, just right on the edge of visible to ultraviolet. So all of these are visible photons. And I just want to do that once again so you can see the systematic way. First excited state to second excited state, first excited state to third excited state, first excited state to fourth, n equals 2 to n equals 6, n equals 2 to ionized, and everything in between. All of these are visible, so we call them the hydrogen lines, hydrogen alpha, hydrogen beta, hydrogen gamma, but the name of the series, the visible photons that hydrogen interacts with, we call that the Balmer spectral series of hydrogen. And putting it all together, here's our emission spectrum of hydrogen. Here's a Bohr model of it. And what are we looking at here? We are literally seeing the energy levels of the hydrogen atom expressed in color. Since how light interacts with hydrogen atoms is by absorbing and emitting light, when we look at a spectrum, we are literally looking at the energy levels of that element. And you can see the biggest jump is this first jump between hydrogen alpha and hydrogen beta, and then each one's smaller, just like we saw on the energy level diagram. So here's our lowest energy one, hydrogen alpha, this nice red color, 656.3 nanometers. Then we have hydrogen beta, gamma, delta, and that's making up our hydrogen spectral series, the visible light, the one that we can see. So now we're seeing hydrogen in emission. We are just looking at how the electron moves around in a hydrogen atom as it interacts with light, the heart of spectroscopy. If we went to helium, it'd be a different set of lines because all the energies would be slightly different, but it's the same game. So there's all the transitions labeled out. So we have in emission 3 to 2 because we're going from high to low. That way we have the line in emission, not absorption. Then 4 to 2, 5 to 2, 6 to 2, so on and so forth. Which tells us finally what we've been after. What the heck was going on with Kirchhoff's laws? Why do we see an absorption spectrum whenever we have a rainbow of light, a continuous source, and then that light passes through a cloud of gas, a cooler foreground cloud of gas? So let's take a continuous source. Here's the full rainbow, say a nice bright star, and then we'll have an intervening cloud of gas. Let's just fill it with hydrogen atoms. Here comes all the wavelengths of light that are thermally emitted as a blackbody spectrum. They enter the cloud of hydrogen gas that's full of hydrogen atoms. They have electrons and all sorts of different energy levels. So we send in all the red light that's coming in. It's going to find a hydrogen atom that has its electron in the first excited state. That electron is going to go, I like 1.9 electron volts of energy. The color 656.3 nanometers, that color of red, is what I'm looking for to get excited about to move from the first excited state to the second excited state. So that color is going to get absorbed. It's going to get pulled out of the rainbow to excite the electrons in the hydrogen atom, to move those electrons around. Colors that are, say, a little bit longer wavelength, so lower energy, 1.8 electron volts, hydrogen doesn't care. The electron does not like that flavor. The electron in the hydrogen atom does not like that flavor, so it goes straight through the gas, doesn't get absorbed. It's only the very, very specific ones, the colors, the only specific wavelengths, the only specific energies that hydrogen will interact with, they get removed. So we have our hydrogen alpha, we have our hydrogen beta, gamma, so on and so forth. So if we're looking at the light after it goes through the cloud of gas, we only see the light that survives. All the colors that hydrogen absorbs, that hydrogen interacts with, gets removed, and we see an absorption spectrum. The flip of that is here we have a cloud of hydrogen gas. It's full of all sorts of excited electrons. Some electrons are in the 5th excited state, some are in the 2nd excited state, some are free, and you have ionized hydrogen going on with free electrons. Some of them are in the 8th excited state. With all those excited electrons, they're going to make their way back down to the ground state. And whenever they move from a higher energy level to a lower energy level, they're going to emit those specific wavelengths of light. Pew, pew, pew. And the visible part, anything that's going from a higher energy level down to the 1st excited state, the Balmer series, the visible photons, that's what we would see. So we point our telescope with a spectrometer on it, and we would look at this cloud of hydrogen gas, and we would see the emission spectrum of hydrogen. Kirchhoff's laws explained. All right, so we have done the hard work to understand the core spectroscopy at this point. This spectroscopy revolutionized astronomy. The ability to do this allowed people like Cecilia Payne-Gaposchkin to figure out that the stars themselves are made out of hydrogen and helium, to figure out what the universe is made out of, the chemical composition of the universe. And actually understanding the details about how these electrons are moving around between these energy levels gives us a way to do an accounting to say, hey, there's this much hydrogen versus this much helium. So it's not just these elements are there, it's these elements are there and there is this much of each one, the relative abundances. So we can see what things are made out of and know what they're mostly made out of, secondarily made out of, 3rd most abundant, 4th most abundant, all because we understand spectroscopy now. We can tell what everything in the universe, as long as it's creating an emission or absorption spectrum and we can measure it, we can tell you what it's made out of. Perhaps we want to take a look at Venus and we want to see, go to the microwave part of the spectrum where we know that this weird gas, phosphine, absorbs light. And we look at the absorption spectrum of Venus and that microwave part of the electromagnetic spectrum, and we see that that wavelength that phosphine likes to absorb is not there. We see an absorption feature at that wavelength in the upper atmosphere of Venus. So astronomers come to the conclusion that phosphine gas exists in the upper atmosphere of Venus, which makes everybody go, wait, what? The only ways that we know of phosphine gas being produced and the levels, the abundances that we see in Venus requires anaerobic life. That's not saying that it is anaerobic life that created it. It's just that's our only known mechanism for the levels that we observe spectrally in the atmosphere of Venus. Are there other pathways, other chemistries that could create it? Yeah, likely. So it's not the smoking gun of life, but it's definitely intriguing. This is why everybody's been so excited, because they understand spectroscopy. They used it to detect phosphine in the atmosphere of Venus. I'll leave us there. I'll see you in the next video.